Welcome to Introduction to Quantum Field Theory, Lecture 12. In this lecture, I will discuss on how to set up an interacting quantum field theory and the technique of perturbation theory in order to get approximations for those interacting quantum field theories. As a review, in Lecture 7, we found that we can write down the partition function for a quantum field theory with a single scalar field as the path integral over d phi of the exponent of the classical Euclidean action. The action SE is the classical action that corresponds to the relativistic field theory that we want to consider, and we limited our discussions to theories that have two derivatives of the field phi appearing in these actions. In Lecture 9, we then proceeded to calculate the partition function Z for free quantum field theories, meaning those where the potential phi, V of phi, is equal to 2 powers in the field phi. In this lecture, I want to now discuss how to set up interacting quantum field theories. Field theories that contain terms other than constants, phi to the 1, constants, phi to the 0, linear terms, phi to the 1, or quadratic terms, phi to the 2, these will be theories that we call interacting quantum field theories. It's possible to also consider other functional forms for the potential, such as an exponential or logarithm, but for simplicity, I will restrict my attention to those theories that have V of phi be proportional to phi to the power n, where n is an integer. Also, for better understanding, I will want to classify the contributions that are possible for V to the phi according to their mass dimension. Recall again the form of the Euclidean action. On the one hand, we have that the Euclidean action is given by an integral over spacetime, dx4, times an integrand that depends on the field phi. The action appears in the exponent, so that means that the action has to be dimensionless. I'll write this as bracket of action equal to 0 for mass dimension 0. Since it is equal to an integral over space-time dimensions, a space-time dimension is an integral over x. X has dimension of length. Length is inverse energy, so each integration over space or time is equal to an inverse mass dimension. In our case, we have 4 of those, so that means that the integration measure counts as minus 4 mass dimensions. If that's the case, and it's also the case that the mass dimension of S is 0, this implies that the integrand, everything that's appearing in the bracket in equation 12.4, must have mass dimension 4. This implies that both of these terms that appear in the expression in 12.4 must have mass dimension 4, meaning dA phi must have mass dimension 4, and the potential must have mass dimension 4. The derivatives are 1 over length, so that's the same as unit of energy or unit of mass, so derivatives have mass dimension 1. If you plug this into the left-hand side of equation 12.5, we have 2 derivatives appearing here, that's mass dimension 2, and 2 fields which basically have to together make up the mass dimension 4. So we subtract the 2 mass dimension on both sides, and then we find that the field phi has to have mass dimension 1. Note that all of our discussion so far has been for the classical field theory. Once we plug that into the path integral, we get the corresponding operator that corresponds to that field or combinations of field that we discussed. The mass dimension in the classical field theory is something like a naive mass dimension. The reason for that is that once we get the corresponding operators in the quantum field theory, the operator mass dimension may get some quantum corrections, and it may differ from the naive mass dimension. However, the naive operator dimension is a good starting point for our setup. Returning to the main story, we have the field phi having mass dimension 1 and the potential having mass dimension 4, So an obvious choice for the potential in 4 dimensions is to say that V has to be equal to phi to the 4 times a constant lambda. This lambda has to be dimensionless because the mass dimension of the potential is already completely fulfilled by the 4th power of the field. So the coupling in 4 dimensions for this theory is dimensionless. If an operator has mass dimension exactly equal to the number of spacetime dimensions, the coupling for that operator has to be dimensionless. For our case, that was the case for phi to the 4 having a coupling lambda that is dimensionless in 4 dimensions. And a different nomenclature for these special operators is to call them marginal operators. By contrast, operators that have mass dimension less than the number of spacetime dimensions are called relevant operators. An example for a relevant operator would be an operator like phi squared that has mass dimension 2. 2 is less than 4, so this would be a relevant operator. Again, by dimensional counting, the coupling for these relevant operators must have positive mass dimension. And for the example at hand here, that's just mass dimension 2. In our case, that operator coupling is just simply called the mass squared. Finally, we can also discuss operators that have mass dimension exceeding the number of spacetime dimensions, and we'll call these irrelevant operators. This nomenclature involving relevant, marginal, and irrelevant operators is important in the context of renormalization group, and we'll come back to those nomenclature once we are ready to discuss renormalization group in quantum field theories. For now, let us return to our main story of setting up interacting quantum field theories. A good starting point for setting up an interacting quantum field theory is to be starting with these marginal operators. Don't be fooled by the name. Turns out that marginal operators are the most important operators to consider for setting up these quantum field theories. For the case at hand in 4 dimensions for a single scalar field, we'll write down the potential involving the term that we had before, m squared phi squared over 2, and then add this marginal operator phi to the 4 with a dimensionless coupling lambda. And we'll take this form of v to the phi as a poster child for an interacting quantum field theory. Once we've set up the potential, we will try to come up with methods on how to solve such an interacting quantum field theory. This has the added benefit that for the case of setting lambda equal to 0, that term just vanishes, and we are back at the free quantum field theory that we solved in lecture 9. With the potential fixed by this particular form, the interacting quantum field theory is then defined as the path integral over the exponent of minus the Euclidean action. And I've split the Euclidean action into 2 parts. There's the part that corresponds to free field theory that we've discussed before. So this is just the quadratic part in the field. And then the remainder, which I call SI for interacting action, that is the part that contains now this phi to the 4 term that we discussed earlier. In the following, I will restrict our attention to coupling values lambda being greater or equal to 0, simply because if lambda is smaller than 0, then the integral over phi typically does not converge. The theory does not exist. However, if we take this restriction that the coupling has to be positive or equal to 0, then at least the discretized path integral are just integrations over phi. All of these integrals exist, and the partition function discretized at n sites is well defined for any finite number of n. Unfortunately, however, the interaction term Si is not quadratic in the field phi. So once that's the case, Fourier transforms, those that helped us solve the free partition function, are not going to do the trick of solving the interacting quantum field theory with a quartic coupling phi to the 4. The math for solving non-Gaussian integrals simply has not been invented. So instead of trying to get an exact result for the interacting quantum field theory partition function z, we will simply lower our goal. Instead of getting an exact result, let's at least try to get an approximation for z that captures some of this interacting part of what we sort of try to set up in this quantum field theory. So what we are trying to do is we are trying to approximate this partition function here that has these two parts, using the fact that if we neglect Si, we were able before to solve the free field theory, meaning we were able to calculate path integrals that involve just e to the minus s0. Obvious trick that we can try to do is we can try to expand the exponent or the exponent of this interaction part such that we get z is equal to the path integral of e to the minus s naught times 1 minus si plus 1/2 si squared, and so on and so forth. The first part here where we have a 1, this integral here is just a free partition function, and we can pull this out of the sort of expansion here such that we get that the interacting quantum field theory is given by the free partition function times 1 minus what I call the expectation value of Si plus 1/2 expectation value of Si squared, and so on and so forth, whereas these expectation values are simply defined as the path integral of whatever the expectation value we are trying to calculate times e to the minus s naught, the whole thing divided by the free partition function. Because we are expanding the exponent of something that's proportional to the coupling lambda, what we'll get for the series for the interacting quantum field theory partition function is a power series in the coupling lambda. For small lambda, indeed, we can treat the interacting term Si as a perturbation around Se, so we call the series that we sort of set up the perturbative series. It's not guaranteed that this perturbative series converges. In fact, for many interesting examples, one can make the case that the series is actually a divergent series. However, it's also true that for many of those cases, we find that the series, even though it's divergent, is at least asymptotic. Assuming that the series is asymptotic, we can use the perturbative series and approximate the interacting quantum field theory whenever the coupling lambda is much smaller than the typical number of terms we keep in these series expansion. So now, how does this work in practice? The first order in perturbation theory, the partition function is given by z1, where 1 now denotes the order in perturbation theory that we are working. And that just means we keep the first term in the exponent, in the expansion of the exponent. So that is just the expectation value of the interaction action. We can plug in the explicit result for this interacting part here. That's just the integral over phi to the 4 expectation value of. So obviously, in order to get a result for the interacting, for the first order perturbation theory, we need to calculate the expectation value of the 4th power of the field. And we'll learn a technique on how to do this in lecture 13. This technique is called Wick's theorem, and this will allow us to break these expectation values into easier parts, which we then can readily calculate. So assuming that we'll learn a technique on how to do this, let's just proceed and set up higher orders in perturbation theory. In particular, to second order in perturbation theory, we get that the partition function is equal to the free partition function times 1 minus Si plus 1/2 Si squared. We can again plug in values for the interaction action directly, and we find that at second order, we now have an integral over x and y of phi to the 4 of x, phi to the 4 of y. Clearly, in order to calculate the second order perturbative result, we'll need to calculate an expectation value of phi to the 4 of x, phi to the 4 of y. Once we have a perturbative result for Z, we can then go on and calculate derived quantities in perturbation theory. What that means is that if we, for instance, want to calculate the pressure to third order in perturbation theory, we start by writing down the basic thermodynamic relation that gives us the pressure, assuming that we have a result or an approximation for the partition function Z. We plug in this perturbative series for Z. So we get the log of C3, C1, C2, and C3, depending on which order in perturbation theory we are working. Since we wrote the third order perturbative result as a product of Z3 and something else, the logarithm separates into two parts. There's the logarithm of the free partition function and the logarithm of everything else. And the first part here is just the free pressure. So that's the pressure that we calculated in lecture 9. And everything else is a correction term on that free pressure. Since these individual terms correspond to powers of lambda, lambda to the first power, lambda to the second power, lambda to the third power, we can again do an expansion of the logarithm of a power series as a power series in lambda. And we find the first order in perturbation theory for the pressure P3 plus 1 over beta V times minus SI from the expansion of the logarithm to first order. Then we have a correction term to second order, and we have a correction term to third order. This means that the expansion for the partition function to third order perturbation theory then gives rise to perturbation theory for the pressure to third order in perturbation theory, and by construction, this result for the pressure in perturbation theory is also a power series in lambda. It might look more complicated than the result for the partition function, but it will turn out that expanding the logarithms in perturbation theory, these combinations are actually simpler to calculate or have some simplifications inbuilt in them, which we'll discuss once we talk about how to actually calculate these properties here. And that concludes the present lecture.